Hello, my name is Ryan Zbikowski, and I'm presenting my research titled Bootstrapped block Lanczos, a large dimension eigenvalue problem. Before I get started, quick shout out to the CSRC staff, my advisor, Dr. Kelvin Johnson, and the Department of Energy for making this research possible. All right, let's dive on in. One of the most pragmatic eigensolvers out there is the householder method, which works by reducing a matrix in a tridiagonal form using a sequence of unitary transformations. But for very large matrices, this approach is impractical due to the large number of iterations required for the method and the massive memory requirements because you're doing full diagonalization. If one is not interested in recovering all the eigenvalues, though, there are better choices. On this slide, I have a visual breakdown of the Lanczos process, which is surprisingly simple, but does a good job of finding extremal eigenvectors. The input matrix is iteratively constructed in a new orthonormal basis called the Krylov subspace, and this tridiagonal matrix converges rapidly to the extremal eigenvalues of the large sparse matrix of interest. One can typically get the lowest few eigenstates in a couple hundred Lanczos iterations from my prior experience. So one completely avoids the need to diagonalize the full model space in this case. Now let's go ahead and check out the block Lanczos method. Our research deals with very large sparse Hermitian matrices. And by large, I mean dimension exceeding 2 billion or more. And by sparse, I mean maybe 1 in a million matrix elements are non-zero. Such sparsity means indices are often far apart, and this leads to issues with load balancing and data locality. To combat this, we use the block Lanczos algorithm, which helps amortize the cost. The main difference in the two methods is instead of applying H to a single vector, we apply it to a block of vectors. This requires more overall, mat-vec operations, but the improved data locality speeds up the time to solution. Bootstrapping Lanczos comes from the idea of instead of choosing a random pivot vector, one can compute an approximate low-lying eigenstate in some truncated model space, then project that vector into the target model space and use that as a pivot for Lanczos to hopefully improve the convergence properties. Bootstrapping block Lanczos just means that we start the block Lanczos pivot off with a set of approximate eigenvectors we believe to be represented in the target model space. Before I talk about my results, though, I want to talk about nuclear structure a little bit more. Our research focuses on solving the time-independent many-body Schrödinger equation, which is often cast as a large matrix eigenvalue problem. We're interested in recovering a small set of low-lying eigenstates specific to different nuclear Hamiltonians. These extremal eigenstates correspond to low-lying nuclear excitation spectra, as you can see in the plot of 8 beryllium to the right. And if there's a strong overlap with our pivot approximate eigenvectors in the pivot block, and the eigenstates in the full space, one sees substantial improvements in the time to solution of block Lanczos through the reduction of Lanczos iterations. All right, let's check out those improvements. So I have two cases to present here. I have each case is a plot of mat-vec and mat-mac timing for each Lanczos approach, and a lower table with the Hamiltonian vector multiplication time and nanoseconds per operation per iteration. Plots A and B show the total mat-vec time for each Lanczos method required to converge a quantity of low-lying eigenstates equal to the block size. So if you want 4 eigenstates or 8, you're going to have a block size of 8 and 4. Truncations 1 through 3 are the bootstrap block Lanczos calculations, where they're labeled by the dimension of the model space used to compute the pivot approximate eigenstates. So we purposely choose these to be quite small relative to the total dimension of 6 million and 141 million respectively. So we can see that block Lanczos does in fact beat single vector Lanczos pretty considerably on its own, and that's clear down here in these tables. And but we see that bootstrapping, in fact, is substantially better than even the regular block Lanczos. So look forward to having you come down to the ACSESS poster. So thank you for your time.